delta over 2, right? Because it's 0 everywhere else. Okay? So this is how you set up the problem. Okay? Q squared 1 over delta dq. Okay? Going from negative delta over 2 to delta over 2. And you work out the integral, you come up with this magical formula. Okay? Delta square over 12. Delta square over 12. So this is the mean square quantization error. Okay? With all the assumptions that we made. Okay? This is significant because, as you can see, the error decreased, okay, with this square here, when you need linearly decrease delta. Right? So just improving delta a little bit, you reduce the error by a whole lot. Okay? Because this has a square sum. Okay? So it's critical to have obviously a small quantization bin. However, with a small quantization bin, we're going to increase the bit rate. So that's a trade-off. Yeah. Now, this is 1/3 of x squared max 2 to the 2b, and then the observation is this. If I increase b, which is how many bits I allow you to use for your quantizations, okay, I increase b by 1 bit, I double the amount of intervals, right? If I allowed you to have 1 more bit for your quantizer, okay, 1 more bit to describe the y, okay, I have twice the amount of step size. Agree? Because I double the number of quantization step size, right? So I reduce delta by a factor of 2. Every 1 bit that you give to your quantizer, you decrease the error by a factor of, reduce delta by a factor of 2.
I have a question.
Yes?
We assume that the distribution of delta is uniform.
Adding 1 more bit increase the signal to noise ratio by 6 dB. So this is the famous 1 bit 6 dB gain, okay, in DSP. Let's do another example of quantizer. Okay, designing a 3-bit uniform quantizer for a signal with range 0 to 128. Okay, 3-bit. If you have 3 bits, then you can describe 8 levels. 8 levels. Okay, and you know the range is from 0 to 128. So then delta will be x max minus x min divided by L, which turns out to be 16. Okay? Now this turns out to be 16, so I'm going to index my y level as 0 to 7. Okay? How did I get this? How did I get these magical numbers? How did I get 8? Why 8?
0 and 8.
Right. That's the first, okay, delta is 16. Okay? So my first interval is from 0 to 16, and the midpoint is 8. Okay? The next interval is 16 to 32, and the midpoint is 24. And that's how I get 24. Okay? The maximum quantization error in this case will be less than absolute value of Q is less than or equal to 8. Okay? So this is a very typical setup in practice. Okay? We typically know the range of whatever coming into Q. Okay? We decide how many levels we will need. Okay, and that determines the bit rate, right? Okay, because output Y will be going to the entropy coder, the arithmetic coder, the Huffman coder. Okay, so obviously a small number of quantization levels here will allow you to have more compression. Okay, now several other forms, very popular form of quantization is rounding, flooring, ceiling operators. And I let you figure out, okay, exactly how you would draw the quantization operation. Okay? So let's skip this and let's do optimal scalar quantization. So this is our problem statement. I have a random variable x with a known EDF, fx of x, okay, which I can observe for a long time. and kind of figure out, okay, how x behaves. Okay. The goal is to find xk, which, so what does xk? Xk is the decision boundary. Okay, and xk hat is the reconstruction, the red dots. Okay. So my job is to figure out all the boundaries, okay, and also all the reconstruction, such that the distortion between x hat and x, the mean square distortion between x hat and x, is minimized. Okay, so this is a pretty well posed problem. Okay, now I'm gonna break this problem into two parts. Okay, so the first part is this. Optimal encoder for a given decoder. Optimal encoder for a given decoder. Given decoder means what? You know the red dots. Okay? Somebody implement the decoder. We don't have any choice. We don't have any choice with the decoder. Okay? But we have we can make smart decision at the encoder. Okay? Which means we have to figure out the xk. Find the optimal xk such that the distortion is minimized given a fixed x hat. Okay? Somebody determine the x hat. For example, middle of the interval. We don't have any choice. Okay? So how do we do this? Okay? Which means I have to minimize the x hat, which is the formula that I showed you before. Okay? With respect to x of k. Okay? Now, so any suggestions? How do we attack this problem? What would you do? How do we minimize something? We take the derivative with respect to xk, right? We set it to 0, we find, okay, and then if you want, you can take the second derivative and verify that it's actually a minimum, not the maximum, right? Okay, but we take the derivative with respect to xk, not x hat, xk, okay, and then we set it to equal to 0, okay? So this is non-uniform quantizer under consideration. You can put the xk anywhere you want. They don't have to have the same length, even, okay? So you put any xk, you can put the xk anywhere you want. But the x hat dot, okay, all the red dots are being given to us, okay? And reconstruction can be anywhere, not necessarily the center, okay? Somebody designed this already. So this is the problem, and I'm going to take partial derivative, okay, with respect to the little xk of this guy, okay? Now, what do we need? We need the fundamental theorem of calculus, right? Derivative of, so basically the derivative and the integral kind of cancel themselves out, right? So the fundamental theorem of calculus say that if you have a function fx like this, and you take the derivative with respect to x of fx, which is this interval right here, then you get, so ddx of integral of some constant c with respect to x, okay, f of t dt is equal to fx itself. Okay, so basically you cancel the operation here. Okay, now why do I only pick up these two guys but not the entire? Okay, I have L terms in the summation, right? Okay, why do they all go away except these two? I'm taking derivative with respect to xk. Okay, so the x0 will not come into play, the xl will not come into play. I only pick up xk. Anything with xk I pick up, right? So I pick up one xk, which is the lower guys here, and I pick up another xk terms where it's upper, right? And I have to take this derivative, and if I apply the fundamental theorem of calculus, I will come up with, okay, so check derivative separately, you're going to come up with something like this. Agree? So let's take a little time to let it sink in. Okay? And our goal is to find xk, right? So set it equal to 0, and I come up with, Okay, so set it equal to 0, and I come up with this. Xk is equal to x hat of k minus 1 plus x hat of k divided by 2. What does this mean? Right. It's the midpoint. You should put the optimal xk, okay, is the midpoint between the two red points. Okay, you're given the red points. There's nothing you can do about it. Somebody designed the red points. Okay, that's the way it is. But we have control of the decision interval, and the optimal decision is right in the middle of the two red dots. Okay, so this is called the nearest neighbor rule. Okay, so you take two neighboring reconstruction points, the red dots, and put your decision right in the middle. Okay, so that's the first problem. The second problem is the optimal decoder for a given encoder. Okay, so this is the inverse problem. Somebody already designed all these quantizations interval, and your job is to find the optimal red dots. Okay, your job is to find the optimal red dots so that the mean square error between x and x hat is minimized. Okay, so this is a slightly different problem. Okay. You're given all these xk plus 1 xk here. And you have to take derivative